equal to the empty set, of course, because zeros is in A, so A is not empty set. And in the definition of the submodule, we should have the condition here and also the condition here. So that is easy. Easy to converse. The first you have A is not equal to the empty set. And for every x, y is in A, you have the x plus y in A. And for every x in A, for every r in R, so you take r is equal to -1. In the first section, we prove that the x and then minus r is equal to the minus xr, and then that is belong to and minus x is in A, so that is in A. And then this condition and the second condition and third condition is will follow that A and plus is a subgroup. In the subgroup, and then because that is abelian group, so we have the A plus is an abelian group. Because that is the abelian commutative of the plus is in M, so it should be in A. So subgroup will be follow that the A is also the abelian group. And then you have the condition of module. The condition of module is true for M. For example, for every x, y in M, for every r in R, you have the x plus y, and then r is equal to the xr plus yr. And because since A is subset of M, so this is also true. So x plus y is also true with x, y is in A. Of course, because A is for example, so that is true for the big set, so that is true for the subset. So we have the A is the submodule of M. So I have just proved that the converse. So that is no. I will give. So you remember that is for proving many subset that are the submodule of a module. So for example, first example is very easy, is the submodule that is only 0, and that is a notation of 0 here. Mean that that is 0. And 0 is the submodule of M for every M. And also M is a submodule of M. We always have on all the module, we have two trivial submodule. That is called the trivial submodule of M. Okay, that is the first. Now the second is I give the abelian group. A, here is A, so I say that is, for example, a abelian group C or something like this. So you remember that when you give the abelian group C, mean that you can consider C as the Z module, and then all subgroup of C is Z submodule of CZ. Okay, I can write the Z submodule, or I can say that is the submodule of C. Here is, you can see that in the, if you consider the C is an abelian group, so I say that all subgroup. But if you consider C as a Z module, then we say that the submodule of okay, all every, okay, so sorry, here is every, not all, every. So here is a subgroup, and then here is a submodule. You can check it, that is easy. The third is the vector space. I to say about the abelian group, vector space, and also the rings. So you can see that that is a very important example. So for the vector space, VK, and if the vector space and then you have the subspace, subspace, in the linear algebra, you already study about the subspace, but now you consider V is K module, and then you will receive the submodule. And that are the same. Submodule is equal to the subspace. Because the condition of subspace is similar here, very equal here, is the same. mean that the subspace should be not empty set, and then for every two vector, the addition of two vector belong to the subspace, and also one vector, one number or one here, and then you take the x, the vector space which the number here should be into the subspace. That is the same, and then you have the subspace and the submodule is the same. You have that is very trivial. And the last is ring. R in R, remember it's R in R. And the last is a ring R. Ring R is, you give that is the ring R here, ring with identity. And then you consider as a right R module and also a left R module. And in the rings, you have the subring and also the idean, left idean and right idean. And when you check this, it should be the left idean is a submodule of the left module here, the left idean. And the right idean is a submodule of R. Why? Because what is the condition of left idean? Condition of left idean, for example, you take the I here, and then what is the condition of left idean? The first is I is not equal to empty set. The condition is for x, y in I, and then x plus y should be in I. And the third condition for every x is in I. For every r in R, you should have the xr in I. Now you compare this with condition. Okay, that is the same, because here is we only to change the I, and here is I write A, but if you write here is I, that is the same. Okay, all I, X in I and R in R should be the XR in I. That is only you change the name, but in fact that is the same. So the left idean is the here, and the right idean is a submodule of here. So I know that because in a ring, the left idean is not a right idean. In general, we can say that the left idean and the right idean is not the same. The right idean is not the left idean, and the left idean is not the right idean. In general, so you can for example, in the books, in our books, I show you the right idean is R0, 0. Here is the right idean of R. But that is not the left ideal. Not. Here is a not left ideal. So the right ideal and the left ideal is not the same. You can take out the more detail about this. Okay, so in the books is already writing about this, and then you can check this. Okay, I would like to say, okay, uh, here is I can say that is example. For example, I can say that there's some special submodule. Uh, the first I have some definition. Now I take the MR, and then MR is called simple. Is called simple if M is not equal to 0, and for every A is the submodule of M, then A is equal to 0 or A is equal to M. A is equal to 0 or A is equal to M. To write this, it means that in M, that is only two submodules and two trivial submodules. Mean that, okay, so it means that M has only two trivial submodules. That are 0 and M. We will say that is simple. Mean that, okay, you can see that here is a module M, and then here is element 0, and there are many element here, but the submodule that is only 0 and also M here. Between there is no submodule. There is no submodule. That is only 0 and M. Is a submodule of M. And then we will call it the MR is simple. MR is a simple. So that is the first definition. The second definition is the minimum submodule. We say that a submodule A The submodule A of M, okay, A of M is called miniman submodule, a miniman. A miniman submodule of A if the miniman of A if A is not equal to 0. Maybe the same here. Here is A isn't. And for every B is a submodule of M if B is a submodule but not equal to A, then B is equal to 0. B is equal to 0. Now you can compare two definitions here. Here is also A here, okay, A, and the submodule of M. Okay, I will draw M here. And then A is a submodule of M. And I will call A is a minimal submodule of A if A is not equal to 0. 0 is here. And then for every B is in M, and B is not B is a of course, B is a submodule of A, but not equal to A. Mean that B, for example, here, not equal to A, and then here is B, and then B should be equal to 0. Mean that inside A, that is, there is no submodule except 0. So you can see the definition is the same here. However, the simple we will say with a module name. But the minimum is, I say that is the submodule, minimum submodule. So the minimum is using the name for the submodule, and the simple is the name for the MR. But in fact, that is, there are many things that is the same. Because when R is the submodule of M, A is a submodule of M and minimum, and then I can say that, okay. So when we compare, we can say that if A is a submodule of M and A is a minimum submodule of A, then AR. Now we consider A as a module is simple. It's simple. So the minimum and the simple is the different about the name. Here is for the module, and here A is the minimum. When is the submodule of the module, we will say that the minimum. But okay, so the first definition is is maximum. Okay, I will say that a submodule A of M is called, okay, you can write something like this, a maximum submodule of A if A is not equal to M. Maximum means that A is not equal to M. And for every B in MR, if um, if if A is not equal to A is submodule of B here, then B is equal to M. It can be said that maximum mean that here is M and here is A here, and then A is not equal to M here. And if you take the B is between the A and B, A, B here, B here. But B here is not equal to A, and then B should equal to M. Mean that between M and A, there is no submodule. There is no submodule between A and M. If different with A, then it should be equal to M. Okay, that is called the maximum. So I can take some example here for easy understand. For example, you can take a Z12. Z12, and if you consider that is a Z module, okay, I can arrow it, and then you can see in the books. And then, okay, the Z12, and then the submodule is the submodule you can list is here is 2, that is 2 Z12, 2 Z12, that is you can write that is 0, and okay, you should write this one, okay, but for quickly I write 0, 2, 4, right, that is here. And 3Z12, that is equal to 0, and 3, 6, 9, that is, and 6Z is equal to 0, 6. And of course, 0 is equal to 0. And of course, Z12. And for 4Z, that is equal to 0 for, yeah, okay. So you can draw the same, the diagram something like this. Okay, here is a 0, and then you can write here is 06, mean that 6 z here, and here is 4 z 4z12. Okay, that is a submodule. And then 6, you will have a 3. Okay, here. And then 2 z here. And 6 is, here is a submodule of this one, and submodule of this one. And here is a z12. And 4 is, of course, the submodule of its one. Okay. Okay. So in this case, you can see that here is the 4z12 here, and this one you have a 2 is this one, and this one is the minimum submodule of there is no, so that is the smallest, that is the minimum, that is minimum. Someone in our class is come to very late, so should be waiting for the next hour. I hear some. I don't see in the computer, because now that is whiteboards, but they are come very late, so should be waiting. Okay, here is, and then you can see that is, here is, okay, that is, and that is maximum submodule of Z12, because between here there is no submodule. Okay, there is no submodule. There's no submodule. Okay, that is one example. I show you two minimum submodule. And two maximum submodule. However, I know that the minimum and the maximum, sometimes that is not different. Mean that the minimum submodule is sometimes is also the maximum, and the maximum is also the minimum. Okay, I can write something like this. Okay, for example, Z6, and then you will have the submodule is Z6. The submodule is Z60, and 3Z6 is equal to what is 0, 3. And 2Z6, that is equal to 0, 2, and 4. Okay. 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 Okay, that is that all. And then you can draw that is Z6 here, and then 0 here, and then between is a 3 Z6, and here's a 2 6, and then you have the diagram here, and then here. Okay, so you can consider here that is minimum, because between here there is no submodule, there is no submodule, so that is minimum. Submodule. However, between this one, there is no submodule, so that is also the maximum submodule. Okay, so the 3Z6 is also the minimum submodule and also the maximum submodule. And also in this case, the 2Z6 is also the minimum and also the maximum. Okay, that is some special, and I give you some example about this. Now we have the proposition. Now I give the here is the class, the set of submodule of MR, and I take the intersection of A, which A is in gamma here. So the intersection of submodule is a submodule of MR. The intersection of submodule of MR is also the submodule of MR. This can be easily checked by using the condition criteria of submodule. The characterization you can prove at the homework, because that is you here is you can take it that is B is here, and then you prove that B is not equal to empty set for every x, y is in B. You prove that s plus y is in B, and for every is in B, for every r in R, you prove that is R in B. So you prove at home. I only give you one note that is you should divide by two case. The first case is gamma is equal to empty set, and then the and then you prove that B is a submodule of M that I have written. Okay, I only say to you something like this. And then, but I would like to say before ending the first hour is the union of the submodule is not a submodule of MR in general. Sometimes that is a submodule, but in general that is not submodule. And one of the, so the intersection is okay, but the union is not okay. It's not a submodule. I can give you one example very immediately. For example, you can take the 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 okay. You can take something like r square. This r square here. Here is r square, and then that is the r submodule. So you take a r times 0, mean that that is r0 with r in r. So here is r0 is here. Here is r, okay? And then 0 is equal to 0r with r in r. That is here. That is here. Okay. And the the submodule. But 0 here is not a submodule of r square. Because if you take one element here and one element here, and then you take the the element here, and here is not, for example, here is A, is B, and then here is the element here is AB. AB is not belong to this one, not belong to. So you have the union of the submodule is not a submodule of MR in general. Okay. So we have a rest now, 10 minutes. Okay. Okay, we continue. Um, okay, so now um, now we take the sub module MR. Uh, okay, you hear me, and also to see the whiteboard now.
Yes.
Okay, so let's the right arrow module M, and we take the A is the subset of. Okay, I take for example S is a subset of M. When you take the M here, and then you take the S here. Sometimes S is a submodule of M, and sometimes S is not a submodule of M. It's not a submodule of M. So we back to the criteria of the submodule. Mean that if S is not a submodule of M, then it should be happen not happen is one of three conditions. Is S is not equal to empty set for every x y is in S, should be x y is in S, and for every x in S, R in R, and then XR in S. And then if this happen, so it should be one of the condition here is not true. For example, there is this XY, but XY is not in S. Mean that, or something like this. For X here and Y here, but you tie X, you plus X and Y, and then X and Y is out of S. And also X here and then XR is in here. For example, something like this. Now I collect all the element here. Mean that I extend this one to this one. For the extension here is a submodule of M. And I say that M is generated by S. Okay, I extend. So we have the definition here. The smallest submodule A of M containing S. The smallest. Okay, there are many submodule content. For example, here, and then you have that here, and also M here containing S. But I take the smallest submodule containing S. is called a submodule of M generated generated by S, and denoted by here is A, here is equal to, and then we will write what is the denoted by, okay, something like this, okay, S. Okay, so the smallest submodule mean that you remember that is extension here, extension for this is a submodule, but add is not the submodule, but you extend this one, the smallest submodule, and then is called it the submodule generated by S. Um, and then you will have the proposition immediately, because that is S is equal to what is the intersection of A, and A is containing S, and A is a submodule of M. The submodule containing S, and you take all intersection of all submodule of M containing S, you will receive the the S generated by S. Because okay, I can draw this in not to prove that is easy. Okay, you have the intersection of submodule is a submodule. For example, something here I will draw is S here, sorry, M here, and then SE here. SE here. Now you have the submodule containing SEs here. The submodule containing SEs here. The submodule containing SEs here. Many. And you take the intersection. The intersection is here. Okay, that is because the intersection is the smallest submodule. The intersection is submodule. You have study. The intersection is submodule, and that is smallest because that is the intersection. So that is here. Okay, easy to prove is that is only we only say that is the intersection. Um, Now I give you one example. One example, for example, I say that the Z is a Z module. And I take a 2. S is equal to 2. S is not a submodule of Z. ZZ. Because, for example, you take a Z plus Z is equal to 4, is not equal to S. So what is the 2? We can see here is 2 and 2 is 4. 4 plus 2 is a 6. 6 plus 2 is 10. 2 is 8. 8 plus 2 is 10. So on. Should be belong to the extension. Okay, here is only 2 here, and here is Z. And you have a 0 here, is 1 here, and 2. And then 2 plus 2 should belong to. Here is S only this one. And 4, 6, so on. And 2 belong to, so minus 2 should belong to, minus 4 belong to, so on. So that is 2, 4, and on, so 0. So I write that is a 2Z. 2Z. And you can prove that 2Z is the smallest submodule of M of Z containing 2. That is very easy. Okay. Containing 2. Now I have some definition. I have some definition. Let MR the first if we take a S and then S here is equal to M. Mean that S here is equal to all M. Then S is called generating set. For M. The generating set for M mean that when you take a S, okay, for example, you remember the R square? You can take many examples about the vector space. And you remember that 1, 0 and 0, 1 here is a generating set for R square. For R module, R square. Because that is the base. You remember that is the basics. And in this case, I only say that the generating set the generating set. Okay, the second is if here S is a generating set and S is finite. S is finite. Then M is called a finite generated. Finitely generated mean that the generating set is finite. Is finite. If the S here is infinite, and then we say that that is finite. Example, For example, you can take a Z. Z is generated by 1. ZZ is only generated by 1. And also the R square here is finally generated. Finally generated because that is only 2. Here is finally generated. And then in the case, the S is only one element. Is only one element. Is only one element. Then mean that we can write this as mean that M is equal to the x0, only one element here. Okay. Then M is called M is called a cyclic module. Then M is called a cyclic module. Cyclic same as you have the subgroup. You have a cyclic group. Cyclic form. Okay, and then now I define the independent. The set H is called independent. Is called independent. If for every subset, every finite subset of S is independent. What is the finite subset is independent? For example, S is equal to the S1, Sn, finite. And then independent, you already study in the vector space. That is mean that the S1 and then R1 plus Sn, Rn is equal to 0. Is you follow that? R1 is equal to R2 is equal to so on is Rn is equal to 0. The same as in, and then that is only extension to S is in, if that is finite, then here, but that is infinite, then every subset, every finite subset that is independent. That is independent. And we have the definition same as in vector space, that S is called a basics for M if S is generating set and S is independent. And what is dependent? Dependent that is not independent. And the last definition is dependent mean that they're not independent. Not dependent. It's not dependent. Okay, so I will give you the dependent and not dependent. Okay, for example, okay, I will take a very easy that is Z4 is Z4 0, 1, 2, 3. The Z4 is, you can consider that is a Z module. And the first is plus. Plus is mean that 1 and plus 2 is equal to 3 or something like this. 3 plus 1 is equal to 0 or something like this. Okay, so on. And the second is Z module. So that is Z and tie with 1, 2, 3, and 0, so on. And Z in Z. For example, you take a Z is equal to uh, 11, and then you tie with 2, that is equal to 2, and that is equal to 2. So on. There are many. Okay. But you remember that Z4 is a ring with identity. So that is, you can consider that is Z4 module. So you can see the Z4 is a Z module, but you can see the Z4 is a Z4 module. Z4 is a Z4 module. Okay. The Z4 module is different with Z because Z4 module means that the multiplication is only from Z4. 0, 1, 2, 3, and you tie with here is a Z4 and here Z4, that is only 0, 1, 2, 3. And in case Z module, that is, you can take it here is in Z. 0, 1, 2, so on, and -1, -2, minus. And you tie with here is tied with 0, 1, 2, 3. It's different. The multiplication, okay, that is different. There are two. Okay, so this difference is will be leads us to the difference in, for example, is dependent and independent. For example, in this case, here all element here is in this one. For example, 1, 2, 3 is independent. Why? because, okay, you can take a z in z and you tie with, for example, 10, 2, okay, and equal to 0. Sorry. Oh, sorry. Dependent. Sorry. Uh, so you can dependent because you can take a z is equal to what is z is equal to um, z is equal to 2 2 or 4 or so on. For example, 6 and okay, 6 is equal to 0, but 6 is not equal to 0. So in this case, you have a 1, 2, 3 is independent, and also in this case, 1, 2, 3 is also dependent. 1, 2, 3 is dependent. But in this case, you should explain that is from in this to tie with this one. For example, 2 tie 2 is equal to 0, but 2 is not equal to 0. Here you can take it z in z. For is not equal to 0. But in this case, you only to take the 1, 2, 3. 1, 2 is equal to 2. 2 is here. 3 and tie here is equal to 2. 1, 2, 2, 3 is 2. But, okay, when you explain the dependent, you should say that, oh, 2 tie 2 is equal to 0. However, the 2 is, that is only this one. And 0 is not say here, because 0, of course, tied with 2 is 0. So that is only 4, 1, 2, 3, 4 here. But here is many tied with 2 here. Okay, so that is dependent, but the explanation is different. Okay, so okay, I will stop the lecture this morning here, and I would like to say again. Okay, I will speak in Vietnamese. Về cái việc làm bài tập thì các anh chị sau khi mà kết thúc, vì xong rồi có nhiều người hỏi và hiện nay có một số đã gửi bài cho tôi rồi, thì sau khi kết thúc cái section á, thì các anh chị gửi làm cái bài tập và gửi thành một file cho tôi. Thì cái section 1 và section 2 thì nó ngắn, section 1 ngắn, còn section 2 thì dài hơn, cho nên chỉ là từ đây cho đến khi section 2 các anh chị gửi một lần cũng được, hoặc là các anh chị có thể gửi từng section cũng được. Bây giờ là các anh chị có thể gửi section 1 và ít hôm và tuần sau tôi dạy xong cái section 2 thì các anh chị bắt đầu làm bài tập và gửi cho tôi. Đấy. Sau đó một tuần làm lại rải, nhưng mà thực chất là các anh chị phải làm từ từ. Ví dụ hôm nay xong là chưa hết section, nhưng các anh chị phải làm dần cái số bài tập. Bây giờ ta sẽ làm quiz. Cách thức làm quiz là là trong này thì tôi đã ra là người nào xin ngày chẵn thì làm đi chẵn, người nào xin ngày lẻ thì đi lẻ, và các anh chị không được chẹp nhau. Nếu các anh chị chẹp nhau thì tôi sẽ tôi sẽ không chậm. Và và tôi sẽ gửi cái đề vào trong Zalo, các anh chị mở cái Zalo của lớp ra và nhận bài và làm. Thời gian làm bài là 20 phút, cộng thêm về mấy phút nữa để làm file. Như vậy là chỉ cái đó qua Zalo và đặt tên theo tên của mình qua Zalo hoặc là qua email và gửi lại cho tôi. Để các anh chị là rõ chưa?
Dạ đó.
Ok. Rồi các anh chị đã nhìn thấy chưa? Anh chị đã nhận được chưa? Rồi, và như vậy thì các anh chị làm cho đến 9 giờ. Tức là kể cả làm file hay gì đó là gửi lại cho tôi là 9 giờ. Để bây giờ các anh chị có thể rời khỏi cái meetings, leave the meetings now.